The ground has one job in our minds. It is supposed to stay still. Houses can creak, trees can bend, oceans can rise, but the ground is the thing everything else rests on. That is why an earthquake feels so wrong. It breaks one of the oldest promises our senses have ever learned. But the ground was never truly still. Beneath every street, forest, desert, and ocean floor, Earth's outer shell is divided into enormous slabs of rock called tectonic plates. They are not floating like rafts on water, and they are not racing across the planet. Their motion is slow, usually measured in centimeters per year. But a few centimeters per year, multiplied across an entire continent, becomes a force that can bend mountains, open oceans, and tear faults through solid rock. Most of the time, this motion is silent. A city can sit above a dangerous fault for generations and feel nothing. Buildings go up, roads are paved, children become grandparents. And deep underground, the edges of massive rock blocks keep pushing, sliding, and resisting each other. An earthquake begins with a problem that sounds almost too simple. Two pieces of earth are trying to move, but friction gets in the way. A fault is a fracture in rock where movement has happened before and can happen again. At a plate boundary, or sometimes far from one, blocks of crust may be pulled apart, pushed together, or dragged sideways past each other. If the surfaces were perfectly smooth, they might slide gradually. But real rock is rough. Faults are not polished glass. They are jagged, crushed, folded, uneven, and pressed together by the weight of everything above them. So the plates continue their slow motion, but the fault can lock. This is where the danger grows. The rocks around the locked fault are forced to deform, not like rubber in your hand, not in a way you could watch from the surface, but over kilometers of crust and decades or centuries of time. Rock can store elastic strain. It can bend slightly. It can compress. It can twist. It can be pulled out of shape while still holding together. A useful comparison is a stuck drawer. You pull gently at first. Nothing moves. You pull harder. Still nothing. The force is building, but the drawer remains jammed. Then suddenly it jerks open, not by the tiny amount you expected, but in one sharp motion. The energy you were adding did not disappear while the drawer was stuck. It was waiting for friction to lose. A locked fault behaves in a similar way, but on a scale that is almost impossible to picture. The drawer may be tens or hundreds of kilometers long. The pull may come from the movement of entire plates, and the jerk, when it finally happens, sends waves through the earth. This idea is called elastic rebound. It became especially important after the 1906 San Francisco earthquake, when scientists noticed that the land on either side of the San Andreas Fault had been slowly distorted before the quake and then suddenly shifted. The crust had stored strain, and when the fault slipped, part of that strain was released. The actual beginning of an earthquake is not the whole fault moving at once. It starts at a point underground where stress finally overcomes friction. That point is called the focus, or hypocenter. Directly above it on the surface is the epicenter. People often use epicenter as if it means the place of maximum destruction, but that is not always true. The worst damage can happen away from it, depending on depth, rupture direction, ground type, and buildings. The epicenter is simply the surface point above the starting point. Once rupture begins, it can spread along the fault like a tear racing through fabric. One patch slips, changing the stress on the next patch. That next patch may slip too, then the next, and the next. In a small earthquake, the rupture may stop quickly. In a giant earthquake, it may rip through a huge section of fault. The 2011 earthquake off the coast of Japan was one of the most powerful ever recorded. A massive area of the boundary between tectonic plates slipped, and in some places, the seafloor moved by many meters. That movement shook the ground and displaced the ocean above it, producing a devastating tsunami. The quake was the sudden slip of rock. The tsunami came from the movement of the seafloor and water. When a fault slips, the released energy travels outward as seismic waves. These waves are why a break deep underground can make a lamp swing, a road buckle, or a skyscraper sway. The first waves to arrive are usually P waves, or primary waves. They compress and stretch rock in the direction they travel, a bit like a slinky being pushed and pulled. They are fast, and because they arrive first, modern earthquake early warning systems can sometimes detect them and send alerts before stronger shaking reaches a location. That warning may be only a few seconds, but it can be enough to slow a train, stop delicate machinery, or give someone time to drop, cover, and hold on. After the P waves come S waves, or secondary waves. These move rock side to side or up and down, perpendicular to the direction the wave is traveling. They are slower than P waves, but often produce stronger shaking. Unlike P waves, S waves cannot travel through liquid, which is one reason seismic waves help scientists learn that Earth's outer core is liquid. Then come surface waves. These travel along Earth's surface, and they can be especially damaging because they move the ground in rolling or side-to-side motions. During a strong earthquake, the surface may behave less like a rigid floor and more like a heavy carpet being shaken from below. This is why earthquake damage is not controlled by magnitude alone. Magnitude tells us how much energy the earthquake released, but what people experience also depends on intensity, how strong the shaking is at a particular place. A large, deep earthquake far away may be felt gently over a wide area. A smaller, shallow earthquake directly beneath a city can be much more destructive. Depth matters because waves lose energy as they travel. If the rupture happens only a few kilometers below the surface, the shaking reaches people before much of its energy has faded. If it happens hundreds of kilometers down, the waves travel farther, and surface shaking may be weaker. The ground beneath a city matters too. Solid bedrock often transmits shaking differently from soft sediment. Loose, water-saturated soils can amplify motion. In some cases, they can even undergo liquefaction, where shaking causes the ground to temporarily lose strength and behave more like a thick fluid. Buildings can tilt, pipes can rise, pavement can split. The earthquake did not need to swallow the ground. It only needed to shake the material until it could no longer support weight in the same way. Buildings add another layer. Every structure has natural frequencies at which it tends to sway. If the shaking matches those frequencies, the motion can grow. This is one reason earthquake engineering is not just about making buildings stronger. It is about making them flexible, ductile, and able to absorb energy without collapsing. And then, when the main shock ends, the story underground is still not finished. A major earthquake rearranges stress in the crust. The part of the fault that slipped may have released a large amount of built-up strain, but nearby sections can become more stressed. Broken rock has to settle into a new balance. That is why aftershocks happen. Aftershocks are not echoes in the air. They are real earthquakes, triggered by the changed stress field after the main rupture. They are usually smaller than the main shock, but not always harmless. If a building is already cracked, a smaller aftershock can be the one that brings it down. Aftershock sequences can last days, weeks, months, and after very large earthquakes, sometimes years. There can also be foreshocks before a larger quake. But there is a catch. Scientists usually cannot know a small earthquake was a foreshock until the larger one has already happened. Before that, it is just an earthquake. This is one reason earthquake prediction is so difficult. People have tried to predict earthquakes from animal behavior, gas emissions, tiny tremors, electrical signals, and many other clues. Some patterns can help scientists estimate long-term hazard. We know some regions are more likely to produce earthquakes than others. We can map faults. We can measure plate motion with GPS. We can calculate probabilities over decades. But predicting a specific earthquake with an exact time, place, and magnitude is not something science can currently do. That uncertainty is uncomfortable. But it is also why understanding the mechanism matters. Earthquakes are not random acts of an angry planet. They are the result of physics. Moving plates, locked faults, friction, elastic strain, sudden slip, and seismic waves. The terrifying part is not that Earth is chaotic. The terrifying part is that it is patient. A fault can sit locked beneath a quiet landscape for longer than any human memory. The surface may show only subtle clues: a shifted stream, a straight valley, a scar across hills, a line where the land has moved before. Meanwhile, deep below, stress is being stored grain by grain, year by year. Nothing dramatic has to happen today for something dramatic to be prepared for tomorrow. When the fault finally slips, the energy released in seconds may have been accumulating since before the oldest buildings in a city were built. That is why an earthquake feels sudden to us, but not to the Earth. To the planet, it is part of a long cycle of strain and release, repeated across millions of years. The ground beneath us is not a perfect foundation. It is a moving boundary, a cracked shell, a record of pressure and time. Most days it lets us forget that. It feels solid. It feels permanent. It feels still. Then, for a few seconds, the illusion breaks.
Thanks for watching! If you enjoyed the video, please like, subscribe, and leave a comment below. See you in the next one!